In this investigation, we are going to be taking a look at more growth patterns, more exponential growth patterns. These are going to be a little bit different in that if you read this opening paragraph, this is kind of what we're looking at. We have starting values in our graphs now, because not everything starts at 0 or 1. So when we look at starting value, what does that look like? So for example, right here, that 1/2, that would be your starting value. And these two equations represent the same relationship. So in general, these equations could be written as y is equal to a times r to the x, where a, that is your starting value, or y-intercept, and the r, that is your growth factor or growth rate, okay, so that would be your growth factor, growth rate, and the y and the x, those are always just your variables. So those should always be variables, whether or not you're going to use different variables for those, but a and r, you should have numbers there, and y and x, that's where your variables will always be. By variables, I mean it's going to be a letter of some sorts. So down here, both of these equations, as I mentioned, they are both the same. This one and this one are both the same equations. All right, so we're going to be exploring equations that are more like this one right here. So make sure you have that down, and then also what each part represents. So now let's take a look at killer plants. All right, we're looking at, again, y-intercepts other than 1 or 0. I guess it wouldn't be 0, but 1. And you could think of that y-intercept in terms of population, right? That would be where the population starts. Most populations start with 1 or 2. In this case, in the example that we're going to be doing, it's different. So there's this hyacinth. I don't know how to say that exactly, but it's this plant doubles in area every 5 to 15 days. That's kind of insane how quickly that thing grows. Looks very pretty, but it could take over an area extremely fast and just do terrible things, terrible damage. And so we're going to be looking at something similar to this plant that grows, and we're going to estimate how long it's going to take to overtake this area of 25 million square feet. Okay, so let's look at this. Ghost Lake is a popular site for fishermen, campers, and boaters. In recent years, a certain water plant has been growing on the lake at an alarming rate. The surface has 25 million square feet. At present, that plant takes up 1,000 square feet of the lake. Department of Natural Resources estimate that the area covered by the water plant is doubling every month. So that's extremely important, the fact that it doubles every single month. Make sure these things are written down or that you understand what some of these things. This doubling every month, this is going to represent what we know as our growth factor, or growth rate. As I mentioned up here in this equation, what part of this was our growth rate. And then also this number right here, that's what we're starting with. Before we come in and try to solve any sort of problem, this is what we're starting with. So this is going to represent our starting value, or we also know as our y-intercept. So as you're answering part A, I want you to keep some of these things in mind. And also part B, I want you to keep some of these things in mind. So in part A, write an equation that represents the growth pattern of the plant. Go ahead and try this on your own, and then come back to the video to see how you did. Okay, so for the first one, write an equation that represents the growth pattern. If you remember, the original equation that I gave you was y is equal to a times r to the x, and a was the initial amount. In this case, it starts covering 1,000 square feet, So this is going to be 1,000. And then the growth rate, well, it doubles every month. So the growth rate is 2. So our equation is going to be y is equal to 1,000 times 2 to the power of x. So that would be our equation. Then number 2, explain what information the variables and the numbers in your equation represent. Well, in this case, let's look at the y. We have to explain what the y is, what the x is, what the 1,000 represents, which we've already talked about, and what the 2 represents. If you haven't done this, please pause the video and try this on your own. The y represents the covered area. Okay, that's the total amount that's covered. The x represents how many months. Okay, so if it's after 10 months, you would plug 10 in there and so forth. And remember, this 1,000, that's the starting covered area. And this 2 represents the growth rate or growth factor. Okay, remember this is also, when we go to graph it, that's going to represent our y-intercept. And then compare this equation to the equations in investigation 1. Well, the difference is in investigation 1, we just had ones like this, right? So this is what we had in investigation 1. But now in investigation 2, we have this starting amount right here. Okay, so that's the biggest difference. So make sure in your own words you're able to explain the difference more than what I have here. Write it out in words. Use sentences to help explain. Now let's take a look at B. You're going to be graphing. So before you do this, what I would recommend is that before you graph it, make a table. Right, and so that table, remember y is the amount of area, so that is your dependent. So in our table, we usually put our independent up top and our dependent down here. And this would be, remember, this is the amount of months. The x is the amount of months. So you would start at 0 months, 1 month, 2 months, 3 months, and so forth. And so use that equation to figure out what these are. That'll help you get a graph and then answer the rest of the questions using the graph. So try B on your own and then come back to the video to see how you did. Okay, so first of all, let's take a look at our table. Remember, these are the months. So at 0 months, that's your starting value of 1,000. So on our graph over here, right here, you're at 1,000. When you're setting up your graph, having your table is going to help because remember, this is your dependent, which is your y-axis. That would be this axis right here. And you know it grows really quickly. So just within just a couple months, you're at tens of thousands of square feet covered by this plant. So you have to graph, make sure when you're graphing, you set it up. Like in this case, we're going by 2s all the way up to 16. And then down here, the months just go by 1s. So you can just go 1, 2, 3, 4, however big, however small you went, that would be just fine. So making our table will help us make our graph. So here's our table. Remember, it should show that it's doubling every month, which it is. And then these should also, after 1 month, this should be at 2,000. Through 2 months, 3 months is 8,000. And then 4 months should be at 16 because you're going to be multiplying by 2 again right there. So go ahead and check yours against mine, the graph. And again, I would recommend doing the tables whenever you have to do a graph for exponential functions like this. Let's take a look at number 2. How does this graph compare to the graphs of exponential functions in investigation 1? Well, let's just kind of talk through it. All the ones in investigation 1, this y-intercept was at y equals 1. But in this case, this is not at y equals 1. We start at 1,000 because if you think of the chessboard and the rubas on the chessboard, you start with 1 on the first square or 4 on the first square. right? So it started differently, or 1 on the first square and then 4 on the second, 1 on the first square. It was always 1 on the first square. So this is different because the starting value is something other than 1. But the shape of the graphs are the same because the growth is still exponential. So go ahead and pause the video and answer that, part 2, to the best of your abilities. And then part 3. Recall that a function is a relationship between two variables. Now in this case, remember our two variables were y, right, which was the area covered after m months, and the other variable was m, the number of months that went by. Okay, now there's one dependent and one independent, and there's one independent outcome or dependent outcome for each independent income. Meaning if we look at our table, imagine continuing this, going all the way up to 100 or 100 months, 200 months, 300 months, right? Would there ever be a repeating y value? So would that area of the lake that's covered ever be equivalent to any other month? And if the answer is no, then it's a function, right? There's no time where any y value in here will ever be the same because it is always increasing. Okay? And then also, this y value, okay, that's the area, that was our dependent variable, and the number of months is your independent, because how much is covered depends on how many months has gone by. And then let's take a look at part C. How much of the lake's surface will be covered by the end of the year? Well, our equation was in months, right? And a year has 12 months, so make sure you use the appropriate number of months there. And number 2, how many months will it take for the plant to completely cover the surface of the lake? Remember, the lake was 25 million square feet. Go ahead and answer parts 1 and 2 on C, and then come back to the video to see how you did. So if we look at the first one, remember this is in 12 months. So if we plug in our equation, that would be y is equal to our starting value times our rate, which is doubling, to the power of 12. So you would put this into your calculator, bing bong bong, bing 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 bong, and the area that's covered will be 4,096,000 square feet. All right, so that's the total area that's covered after 12 months. Now remember, that's 25 million square feet for the whole thing, so we're not quite there, but we're pretty close. So for number 2, it should be pretty close, because think about it, if we doubled this, that would be 8, and we doubled that, that would be 16, so it's going to be pretty close. And so if you look at, let's do, I did A, right, so it'd be y is equal to, let's look at the 14th month, is what I came up with, times 2 to the 14. You get 16,384, so 16,384,000 square feet. And then if you go one more month, the 15th month, you get 32,768,000 square feet. And so that is actually over. So we have an under amount, over an amount. So our answer is going to be between 14 and 15 months. So you got between 14 and 15 months to figure this thing out before it just completely destroys the lake and the fish and the wildlife and everything in it. So that is all that we have with 2.1 Killer Plant Strikes Lake Victoria.